Welcome back to AI Paper Podcasts. Today we're diving deep into a paper that's really trying to tackle a challenge we're all facing in AI. How do you boost the reasoning power of large language models without needing a server farm the size of a small country?
Yeah, it's a constant balancing act, right? More parameters, more power, but the computational costs just get out of hand so quickly.
Exactly. And that's where this paper, Interthinking Transformer, Leveraging Dynamic Depth Scaling to Foster Adaptive Internal Thinking by Chen et al., comes in. They're bringing a fresh perspective.
What's exciting here is how they frame the problem. They took inspiration from how we think, how we strategically allocate our mental energy to different parts of a problem.
So instead of treating every word in a sentence with equal weight, they built a model that can figure out which tokens need the most brain power. And just for our viewers who haven't encountered this concept before, tokens can be thought of as individual words or parts of words the model processes.
Right. And the core innovation they introduce is the Interthinking Transformer, or ITT for short. Think of it as a new architecture that lets these large language models dynamically allocate additional computation to crucial tokens using adaptive inner thinking steps.
Such a brilliant concept. And the results are seriously impressive. They show that ITT can achieve the same level of performance as much larger models, sometimes even surpassing them, while using significantly less compute.
And here's the kicker. It does this all while achieving better data efficiency, too. They were able to match the performance of a larger model using only 56.8% of the training data. That's huge for anyone working with limited data sets or who wants to reduce the environmental impact of training these massive models.
Exactly. So for those of you watching the short form edit, that's the essence of what makes ITT so innovative.
Yeah.
Dynamic resource allocation, inspired by human cognition, resulting in a significant performance boost and improved efficiency. But for those of you sticking with us for the full deep dive, let's unpack exactly how they pulled this off.
So the first thing to understand is the problem they were trying to solve. We all know large language models are amazing, but scaling them up gets expensive fast.
And smaller models often struggle with those complex reasoning tasks, simply because they lack the parameter space to truly grasp those nuances.
Precisely. So the researchers started by analyzing how models learn, paying close attention to the flow of gradients during training. Think of gradients as signals that tell the model how to adjust its parameters to improve its performance.
So what were they looking for in these gradients?
Well, they were essentially trying to understand what happens inside the model when it encounters different types of tokens. And what they found is fascinating. Simple tokens, like common words with straightforward meanings, are usually handled pretty quickly in the early layers of the network. But complex tokens, those with multiple meanings or subtle interpretations, cause all sorts of disruptions in the gradient flow throughout the network.
It's like the model is hitting a roadblock and having to work much harder to understand those tricky tokens.
Exactly. They describe these disruptions as gradient spikes. And they're a clear indication that the model needs more computational resources to grapple with those specific parts of the input.
So that's the problem. But how do they translate this insight into a solution? Enter the inner thinking analogy, right?
Yes. They started thinking about the layers of a neural network, not just as mathematical operations, but as steps in a thought process.
So each layer represents a separate attempt by the model to understand a particular token. I like that it makes the whole process feel more relatable.
And it leads to a powerful question. What if we could give the model more thinking steps, but only for the tokens that are causing it to stumble?
It's like giving your AI a cognitive boost, specifically for the hard stuff. Instead of just throwing more processing power at everything, you're being strategic about where that power is needed most.
And that's precisely what ITT allows you to do. It's a new architecture that gives the model the ability to dynamically allocate more thinking steps to the tokens that need them most.
Okay, that's the high-level concept. But let's get into the nitty-gritty. How does this ITT architecture actually work? What are the key mechanisms?
Well, there are three main components to understand: adaptive token routing, residual thinking connections, and thinking step encoding. Let's start with adaptive token routing. Imagine a traffic cop inside the model directing the flow of tokens.
I love these real-world analogies. Makes it so much easier to visualize what's going on.
So this traffic cop, or router network, analyzes all the input tokens and figures out which ones are likely to be the most challenging. It looks for cues in the early layers of the network, like those gradient spikes we talked about earlier.
So it's basically identifying the tokens that are causing the model to think harder.
Exactly. And then, instead of sending all tokens through the same number of layers, It directs those more challenging tokens to additional processing layers. It's like a triage system in a hospital, identifying the patients that need more immediate and specialized care.
Okay, that makes sense. So those difficult tokens get sent down a different path with more processing steps. But what happens to them once they're in those extra layers? Is it just more of the same?
That's where the second key mechanism comes in. Residual thinking connections. These connections are how the model actually performs its inner thinking. Each additional layer isn't just repeating the same process, it's building upon the results of the previous layer, refining the model's understanding of the tokens step by step.
So it's an iterative process, kind of like how we might revisit a difficult problem multiple times, adding to our understanding each time we think about it.
Exactly. And this is where the analogy to human cognition really shines. It's not just about brute force processing, it's about thoughtful, iterative refinement. Each thinking step is informed by the results of the previous steps, ensuring that no information gets lost along the way.
That's incredibly clever. But I'm imagining that if you have all these different thinking steps happening, the model might start to get confused about where it is in the process.
Yeah.
How do you keep things organized?
That's where the third mechanism comes in. Thinking Step Encoding. This is essentially a way of giving the model a sense of context for each thinking step. It's like giving each step a unique identifier, so that the model knows exactly where it is in the thought process.
It's like giving each layer a little label that says, okay, you're on step 3 of trying to figure out this particularly tricky word.
Precisely, and this encoding is crucial because it allows the model to distinguish between the information it's gleaning from different thinking steps, preventing everything from just getting jumbled together.
So we've got our traffic cop directing traffic, our iterative thinking steps, and our handy labels to keep everything organized. Sounds like a pretty elegant solution. But of course, the real question is, does it actually work? Does all of this clever architecture actually translate into real-world performance gains?
That's what we'll explore in the next part of our deep dive. Let's dive into the results. So let's talk results. The authors put ITT through its paces on 11 benchmark tasks, comparing it to traditional transformers and other state-of-the-art methods.
Don't keep us in suspense.
Well, the results are pretty compelling, across a variety of tasks, including language modeling, question answering, and sentiment analysis. ITT consistently outperformed the competition, often by a significant margin.
That's what we like to hear. But I'm curious, how did it stack up against models with a similar number of parameters? Was it just brute force compute winning out?
That's what's so impressive. ITT was often tested against models with significantly larger parameter counts, yet it consistently held its own, sometimes even exceeding their performance.
So it's not just about throwing more parameters at the problem, it's about using those parameters more intelligently.
That's the key takeaway here. ITT demonstrates that we can achieve significant performance gains by focusing on architectural innovation and drawing inspiration from human cognition.
It's a powerful argument for thinking outside the box, isn't it?
Yeah.
Instead of just scaling up, we need to be exploring new ways to make models think more efficiently.
Absolutely. And the implications for the field are huge. This kind of efficiency opens doors for researchers and developers who might not have access to those massive computational resources. They can start experimenting with more powerful models without needing to invest in expensive hardware.
It's all about democratizing access to cutting-edge AI. And let's not forget the environmental impact. More efficient models mean less energy consumption, which is a win for everyone.
Right. Now, you mentioned earlier that ITT also demonstrated impressive gains in data efficiency. Let's dig into that a bit. They were able to match the performance of a larger model using only 56.8% of the training data. That's a remarkable achievement.
It's huge. Especially in domains where data is scarce or expensive to collect, this could be a game changer.
Think about medical research, for example, where you might have limited patient data available, or in niche fields where large labeled datasets simply don't exist. ITT could open up all sorts of new possibilities in these areas.
Okay, so we've got efficiency in terms of compute and data. What about inference time? Does this inner thinking process slow things down at all?
That's a great question, and it's one of the things that makes ITT so versatile. Remember the concept of elastic thinking we mentioned earlier?
Refresh my memory. How does that work again?
Well, imagine you've deployed your ITT model in a real-world application, and you need to balance accuracy with speed. Maybe it's a chatbot that needs to respond quickly to user queries, or a real-time translation system. With ITT, you can actually adjust the number of thinking steps the model uses on the fly, depending on the specific requirements of the task.
So if you need higher accuracy, you allocate more thinking steps, even if it takes a bit longer. But if speed is paramount, You can dial it back without sacrificing too much performance.
That's the beauty of elastic thinking. It gives you fine-grained control over the trade-off between accuracy and efficiency. It's like having a model with a variable brain power setting.
It's seriously cool. It's like having your cake and eating it too. But before we get too carried away with all the positives, let's play devil's advocate for a moment. Are there any limitations to this approach? What are the potential downsides?
Of course, no approach is perfect. And the authors of the paper do acknowledge some limitations. One area that could benefit from further research is the routing mechanism.
The traffic cop we talked about earlier.
Exactly. Currently, the way the router prioritizes tokens is fixed during training. It learns a specific way of allocating thinking steps based on the training data, and it can't adjust that strategy on the fly during inference.
So it's possible that it might encounter situations or data sets where its learned routing strategy isn't optimal.
That's a possibility. So there's potential for future research on making the routing even more dynamic, perhaps allowing it to learn and adapt to different types of input or tasks.
Makes sense.
Anything else?
Another consideration is memory overhead. The residual connections, while crucial for the iterative thinking process, do require additional memory during training.
So if you're working with really large data sets or extremely complex models, memory management could become a bottleneck. Potentially, yes. But it's important to remember that this is a trade-off. You're gaining significant efficiency in terms of compute and data usage. So some increase in memory overhead is to be expected. And the author suggests that this is an area that can be addressed through optimization techniques. They're already exploring ways to reduce the memory footprint of the residual connections without sacrificing performance.
So it's not a showstopper, but something to be aware of when implementing ITT. Now, I can't help but think back to those visualizations we talked about earlier, the ones that actually show the model focusing its attention on different parts of the input. It's almost like watching the gears turning in its brain.
Those visualizations are incredibly insightful. They provide a way to peek inside the black box of the model and understand how it's actually processing information. You can literally see the routing network in action, directing those more challenging tokens to the additional processing layers.
It's a powerful reminder that these models aren't just blindly crunching numbers. There's a real thought process happening. And ITT gives us a glimpse into how that process works.
And what's so exciting is that this is just the beginning. ITT is a proof of concept, a demonstration that we can design models that reason more strategically, focus their attention, and adapt to different situations. It opens up a whole new avenue of research in AI, one that focuses not just on raw power, but on intelligent and efficient use of that power.
It feels like we're on the cusp of a new era in AI, where models are becoming more and more like us, able to think critically and allocate their brain power where it's needed most. But before we get too philosophical, let's bring it back to our audience.
Okay, let's shift gears and talk about the practical implications of this research. What does the Interthinking Transformer mean for all the AI researchers and ML engineers out there watching this?
What are the key takeaways they should be thinking about as they apply these ideas to their own work? Okay, so we've explored this Interthinking Transformer. We've seen how it works. We've seen those impressive results. We even touched on some of the potential limitations, but now let's get practical.
Yeah.
What does all of this mean for our viewers out there on the front lines of AI research and development?
Well, first and foremost, I think this research is like a call to action. It's a reminder that we don't always need to solve problems by simply throwing more compute at them. ITT shows that we can achieve remarkable results by being more strategic, more thoughtful in how we design our models.
Yeah, it's about working smarter, not harder. Yeah.
Exactly. And that's a lesson that applies whether you're working with a massive supercomputer or a more modest setup. ITT kind of levels the playing field in a way. It allows researchers with limited resources to experiment with models and ideas that might have previously been out of reach.
Yeah, and that can only be a good thing, right, for the field as a whole. More diversity of thought, more experimentation, more innovation.
Absolutely. Now, for those of you who are already working with large language models, I think ITT offers some compelling reasons to rethink your approach. The efficiency gains alone are significant. Imagine being able to achieve the same level of performance with a fraction of the computational cost.
Or imagine being able to train a model on a much smaller data set without sacrificing accuracy. That's a game changer for so many applications.
Think about all the time and energy you could save, not to mention the reduced environmental impact.
Right, sustainability is becoming increasingly important in AI, and ITT really offers a path towards more sustainable practices.
Now, beyond the practical benefits, I think ITT also represents a shift in mindset. It's a move away from those brute force approaches and towards more elegant, more human-inspired solutions.
It's about understanding the problem at a deeper level and then designing models that can reason and adapt accordingly.
And that's where the real excitement lies. ITT is just the tip of the iceberg. It's a glimpse into what's possible when we start thinking about AI in a more nuanced, more human-centric way.
So for all of you watching, I encourage you to take these ideas and run with them, experiment with ITT. See how you can apply it to your own work. Push the boundaries and let's see what amazing things we can create together.
I couldn't agree more. The future of AI is bright, and it's up to us to shape it.
Well said. Thanks for joining us for this deep dive into the Interthinking Transformer. We hope you found it insightful and inspiring, and we'll see you next time for another exploration of cutting-edge AI research.
Until then, keep innovating.